Okay, so we already saw that AND and NOT alone are a functionally complete set of operators. And also that it's minimal in the sense that you can't drop either and still have a functionally complete set. Each of them alone is not functionally complete. But are there, so let's pose a slightly different question. Is there any smaller set of operators that's functionally complete, which is not a subset of those two? Is there any other operator which alone is enough to write all expressions in predicate logic? And it might seem at first that wouldn't be possible, right? Because you have just one operator. What can you do with one operator? But it's actually the case. You can do it. With which operator? Well, this is like already kind of hinted by and not being here and being complete. It turns out that NAND is functionally complete. So this operator here alone is enough to write all expressions in predicate logic, all Boolean functions. Where, well, NAND is just not N. Right, let's write the truth table for this. So, what is NAND? The AND queue, we know already how to do. It's 0 everywhere except here. NAND is just not P and Q. Right, that's what NAND means. NAND is exactly the same, has the same truth table, is defined as not P and Q. So, the truth table for NAND is this one instead. So what can I do with that? How can I combine NAND with itself to write any Boolean function? Now, I could try to do this from scratch and find a way to start from a Boolean function or an expression in predicate logic and go straight to writing it in terms of NANDs. But that's not the most practical way. We can use what we already know, and part of what we already know is that we can write any expression using only ANDs and NOTs, right? So if we can write, that's a crucial idea, if we can write ANDs and NOTs using only NANDs, we're done. Because then our recipe will be, well, we want to write some expression in predicate logic using only NANDs. First, we write it using only ANDs and NOTs. And then we eliminate the ANDs and NOTs into NANDs. And we're done. So, but then we still have this problem. How do we write those in terms of only NANDs? So, suppose we wanted to write NOT. Suppose we wanted to write not P, and all we have to work with is NAND. How can we do that? Well, we can start by noticing, we're going to just use the following trick. Notice that P and P is equivalent to P, right? The operator AND is idempotent. That's what idempotent means. It means that when you apply the operator to the same term, P and P, you get it back, right? Okay, so P and P is exactly equivalent to P, and what we want is not P. So we might as well, instead of getting not P, we might equivalently get not P and P, right? Because this is exactly the same as P. Well, but what is not P and P? Well, this is exactly P NAND P, right? That's the definition of NAND. So this is already done. We finished for not. So P NAND P is equivalent to not P. So we already did not. So to finish, all we need now is to figure how to write P and Q. So how can we write P and Q using only NANDs? And again, it's not very difficult. It takes just a little bit of ingenuity. Of course, it is the case that P and Q is equivalent to not P and Q, right? But again, not P and Q is equivalent to P and Q. So what we get here is not P NAND Q so far, right? So we are almost there. But still need to get rid of this not. Aha, but we already know how to get rid of nots. This is how we do it. And again, you need to be very aware that a formula like this doesn't require that P is a single standalone variable. P could be any complicated expression and the formula is still valid. So we are going to apply this formula to this expression to get rid of the not. So what does the formula say? It says that if I have something negated, not P, this is equivalent to whatever this is, NAND whatever this is. So what is my expression to be negated here? It's this part here, right? So I'm going to write this NAND itself. And that's going to be equivalent to the negation of it. So all I need to do is write P NAND Q NAND itself. And that's equivalent to P and Q. So what does that prove? That shows you can always write any expression in predicate logic, no matter how complicated, using only NAND. How would I do it? Well, you already know how to write it using only ands and nots. Then you eliminate the ands and nots using those two formulas. You eliminate the ands using this one, you eliminate the nots using this one, and in the end you get something that involves only NANDs. So maybe we could do an example